Good morning, everyone. I am Dr. Aslesha Bodavula from the Department of Aeronautical Engineering. So, in the course of high-speed aerodynamics, in today's session, we are going to discuss about some of the numericals, that is from the first unit one. Consider for the numerical one, a pressure vessel that has a volume of 10 meter cube is used to store high pressure air for operating a supersonic wind tunnel. The air pressure and temperature inside the vessel are at 20 atmosphere and 300 Kelvin respectively. So, what is the mass of air stored inside the vessel? So, they are asking us to find out what is the mass of air stored in the vessel. So, now what we know, 1 atmosphere equal to 1.01 into 10 power 5 Newton per meter square. See, this one we already know. So, we know the formula P equal to rho RT, right? So, from this one, what we can write? Rho equal to P by RT. So, now what they have told? They have told that if the air pressure and temperature they have given. So, P equal to 20 atmosphere they have given. So, this 20 atmosphere we are going to convert. So, 20 into 1.101 10 power 5 Newton per meter square. So, what is the temperature they have given? P equal to 300 Kelvin. So, our constant value we know 286, right? So, now from there what we can take? We can substitute. So, pressure is 20 into 1.01 into 10 power 5 divided by 287 into 300. So, from there we got rho equal to 23.46 kg per meter, right? So, now total mass stored in the inside the vessel, what you can write? M equal to V into volume into density. So, that is nothing but volume they have given 10 meter. So, 10 into, so what we got the density? 23.46. So, from there, total mass stored inside the vessel is, 23.234. So, 234.6 kg. So, this is the total mass stored inside the vessel. So, coming to the second numerical, calculate the isothermal compressibility for air at a pressure of 0.5 atmosphere. They are asking us to calculate the isothermal compressibility for air at pressure 0.5 atmosphere. Okay. So, before going to that one, so what we know? Tau T equal to minus 1 by V, dou V by dou P at temperature. So, what we know? V equal to, PV equal to RT, we know, right? So, from there V equal to RT by P we can write. So, if you are considering dou V by dou P at T equal to minus RT by P square. So, what we know? We know tau T equal to minus 1 by V dou V by dou P at T. So, we know dou V by dou P is nothing but minus RT by P square. So, we are going to substitute that inside the equation, and V, what we know? V we know as RT by P, right? So, if you are substituting, what it will be there? Tau T equal to minus of V is RT by P. So, then it will be P by RT into, so dou V by dou P at temperature constant T is nothing but minus RT by P square, right? So, now RT get cancelled out, 1 P will be getting cancelled out, and minus into minus plus. So, tau T equal to 1 by P. So, now what we got? Tau T equal to 1 by P, right? So, what we are asking? So, we are asking that we are finding that isothermal compressibility for air at pressure 0.5 atmosphere. So 1 by 0.5 equal to 2 atmosphere. So now from the international standard of units, P, what we can write? So 0.5 atmosphere to 1.01 into 10 power 5 newton per meter square. From there, it is nothing but 5.05 into 10 power 4. So now tau T equal to, again substitute, it is nothing but 1.9 into 10 power minus 4 Newton. So if you are taking the English engineering system, so then it will be equal to 0.5 into 2116. So that will be 1058. So again 1 by P, if you do, we will be getting the 9.45 into 10 power minus 4 square. So coming to the numerical 3, so we will be considering the same with the numerical 1 example only, but extra what we are doing. So in the previous one, we have calculated the total mass, right, in the numerical one. So in that one, what they have considered, they considered the pressure vessel that has a volume of 10 meter cube and used to store at high pressure air for operating supersonic wind tunnel. So if the air pressure and temperature 20 atmosphere and 300 K respectively. So in the numerical one, they asked us to find out the total mass stored in the vessel. So now in this particular example, they are asking us to find out to calculate the total internal energy of the gas stored in the vessel. So previously it is total mass. Now they are asking us to find out what is the total internal energy. Okay. So now what we know? E equal to CVT we know. So now CV is nothing but R by gamma minus 1. So R is 2827, gamma is 1.4 minus 1. So from there CV equal to 7175. Okay. So E equal to CVT. So that is nothing but 7.5 into 300. So that is E. So now what we know? This particular one, rho equal to RT we know. So from there the mass value which we have already previously calculated, the same thing, rho equal to P by RT. So P equal to 20 into 1.101 into 10 power 5 divided by 287 into 300. So we will be getting to 23.46. From there total mass is nothing but, so V into P, that is 10 is the volume, and P value, so density value we got 23.46. So from here it is nothing but 234.6 is nothing but mass. So previously what we have considered as the internal energy. So if it is total internal energy is mass into internal energy. So 234.6 into, so we got 21 internal energy 53 into 10 power 5. So it is nothing but 5.05 into 10 power 7 joule. So this is the total internal energy we got for the internal energy of the gas stored in the vessel. So we have calculated the mass, total mass stored in the vessel, and total internal energy stored in the vessel. So now next problem what we are doing here, same condition only. So volume is 10 meter cube, and it is again is stored for high pressure air for operating the supersonic wind tunnel. So pressure is 20 atmosphere and temperature is 300 Kelvin. Now what we are doing, we are considering, let us now heat the gas in the vessel. So whatever the gas inside the vessel is, we heat it. So enough heat is added to increase the temperature to 300. So what is now we are telling the 300 Kelvin's temperature is there, right? So we are going to heat the vessel such that it will be increasing temperature to 600 Kelvin. Now calculate the change in entropy of the air inside the well. What is the change in entropy is there? We are asking us to find. So what is the vessel has constant volume. Hence, as the temperature is increased, the pressure will also be getting increased. So what we will be taking 1 as before heating and 2 as after heating substitutes. Okay. Now we know the relation T2 by P1 equal to T2 by T1. So what is T2? 600, right? So T1 is 300. 2. So P2 by P1 equal to 2. Now we know CV, right? CV equal to R by gamma max. So CP is nothing but CV plus R. So we have 7 5 joule per kg Kelvin. So this is the CP value. So now what they were asking us to find out? Entropy change, right? So S2 minus S1 equal to Cp into ln of T2 by T1 minus R into ln of P2 by P1. So this relation we already know. So what we have, we know the Cp value, we know the T2 by T1 value, we know the R value, we know the P2 by P1 value, right? So now what is Cp? Is 4.5 into ln of 2 minus 287 into ln of 2. So that is nothing but 497.3. Okay. So this is the entropy. So now what we have to find out? They are asking us to find out total entropy change. So now for that one, we required the mass. So we already calculated the mass. So that we got 234.6 kg, right? So now change in entropy is capital S2 minus capital S1 equal to n into S2 minus S1 smaller case. So that is equal to 234.6 into 497.6 Okay, so this is the same problem where we are having the pressure vessel have the volume of 10 meter cube. It has been stored for operating the supersonic wind tunnel. Air pressure they have given 20 atmosphere, temperature they have given 300 Kelvin. But we are heating the gas vessel so such that the 300 Kelvin has been increased to 600 Kelvin. Now we have to find out what is the change in entropy inside the vessel. So the change in entropy we got 493.7 and total entropy change inside the vessel we will be multiplied by the mass into that entropy change. So we will be getting 1.167 into 10 power joule per Kelvin. So coming to the fifth numerical, calculate the isentropic compressibility for air at pressure 0.5. So compare the result with that for the isothermal compressibility. So previously in the numerical 2 we have find out the isothermal compressibility, right? So what we are doing here they are asking us to find out the isentropic compressibility for air at pressure 0.5 and compare with the isothermal compressibility which we have already obtained. So isentropic compressibility tau is equal to minus 1 by V dou. So what we know, V equal to minus 1 by rho, right? So from there tau is we can write as 1 by rho into rho by 2. So now when isentropic process V2 by P1 equal to V2 by 1 over tau into P into C into rho. So where C is constant. So we take it, then is equal to what it means into gamma into rho gamma minus gamma, right? This further we can write it as C equal to what we can write from there? C equal to K by rho gamma. So now C value V by rho gamma into gamma into rho into power minus 1. So now what we can write in this one? Rho gamma will get cancelled out. By rho gamma into gamma. So this we can write it as rho gamma by rho. So rho gamma will get cancelled out. So then what we will have gamma by P by rho is nothing equal to S value, right? So now tau is equal to 1 by rho into dou P by dou P of S. So this one we can reverse, we can write, right? So that is nothing but 1 by rho dou P by dou rho inverse. So what is this one? Dou P by dou S? We can write it as gamma P by rho, right? So further tau is equal to 1 by rho gamma P by rho into 4 inverse, right? So now tau is equal to 1 by rho into gamma P by rho inverse. So now from this one, what it will be the reverse if it will happen. So then it will be 1 by gamma P is the tau is value. So tau T equal to 1 by P. So then what we can write? Tau is equal to tau T by gamma. So here what we can write? We can write tau T which is there. It will be changing in terms of with the gamma variation, right? So from what we found for this one, so what we found the tau T is tau T equal to 1.98 into 10 power minus 5 meter per square Newton. So now from here, so tau is equal to 1.98 into 10 power minus 5, but gamma is nothing but 1.4. So that is 1.41 into 10 power minus 5 meter square per n. If you see what it is there, so tau s is small when compared to tau t by gamma times. So tau s into gamma into tau t. So it is compared to the tau s is small compared to the tau t by gamma times. So from here we have found out what is the tau s value, that is isentropic compressibility value, what it is there, and we have compared the results with the isothermal equation, right? So these are the numericals which we are from the first unit, some of the numericals. So again, these numericals have been taken from the modern compressible flow with historic perspective here by J.D. Anderson. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.